This is the first of 3 pre-recorded lectures on solutions, and this first one has a lot of vocabulary and just introductory concepts about solutions. And the first thing that I want to remind you about is what a solution is. It's actually a type of mixture, but it is a homogeneous mixture, meaning that if you are to look at a solution, it is uniform, the composition is uniform throughout. You can't, I like to say, see any lumps, bumps, or layers in it. So solution is a homogeneous mixture. Again, to refamiliarize you with the vocabulary, the substance that you dissolve into something else is called the solute. So if you were making salt water, the solute would be the salt. And the substance that's doing the dissolving is called the solvent. Something like salt water, it's easy to distinguish what the solute and solvent are, but some solutions it's not so easy. So please make a note of the fact that the solute is always there in the lesser amount, the smaller amount. So if all you have are amounts, the one that's present in the largest amount is called the solvent. So just to show you all the different types of solutions there are, because a lot of people think that they can only be in the liquid state, air itself is actually a solution, and nitrogen is present in the largest amount, so nitrogen is the solvent in air. Of course, we're pretty much all familiar with liquid solutions like salt water. The alcohol that people drink is a liquid-liquid solution. And you can also dissolve gas into a liquid, and that's what our carbonated beverages are. The CO2 gas is dissolved and soluble in the liquid portion. And then, of course, we can also have solid solutions. So those are called alloys if we mix 2 metals together and they're homogeneous. Brass is actually a solid solution of copper and zinc. Okay, again, we're still talking about terminology, so if you read or hear the term aqueous solution, it implies that water is the solvent, and that's true of a lot of solutions we'll talk about. And as I said a few minutes ago, air is actually a solution. Nitrogen makes up by far the bulk of air, so nitrogen is the solvent in the solution of air. And you can have more than one solute, okay? Oxygen, CO2, etc. All of those are solutes in the solution of air. Okay, the process of dissolving is actually called solvation. This is a relatively important concept, so make sure that you understand it. And I'm going to go over this in more detail in this lecture, but not everything will dissolve in everything else, which you well know. Oil will not dissolve in water. And what that depends on is how attracted the solute and the solvent are to each other. In order for a solute to dissolve in a solvent, there have to be some really strong intermolecular attractions between the two. So if there are attractions between the solute and solvent, that is called solvation, and dissolution will occur. Solubility, that implies the maximum concentration. So there are reference books with tables of solubility, and if you look up those solubilities, they give you the maximum amount that will dissolve in a particular solvent, usually at a particular temperature too. We have some qualitative concentration terms: saturated, unsaturated, supersaturated. It's important that you know what those mean too. So saturated is the solubility point. That is the maximum amount of solute that will dissolve in a solvent. Unsaturated means you can dissolve more if you want it. So think for a minute, how would you, if I handed you 2 containers of salt water, how would you, and said which one of them is saturated and one of them is unsaturated, how would you determine in the lab, without any fancy equipment, which one was saturated? You'd simply continue to add salt to both of them, And the solution where more solute will dissolve you would determine is unsaturated, and the solution if you added more solute and no more dissolved, that would be termed already saturated. Supersaturated to me has always sounded like an oxymoron, like, okay, if saturation means it's holding as much as it can, what the heck is supersaturation? You can essentially trick a solution into dissolving more than it should, and the next slide kind of goes over. So what you do is, you probably know intuitively that most solutions, as you heat them up, you can dissolve more solute. And so let's say you're making salt water at room temperature and you've dissolved as much salt as possible, and then you put it on the stove, you start heating it up, and you can start adding more salt. Well, if you then get a lot of extra salt in and you cool very carefully and don't disturb at all this solution back down to room temperature, sometimes all of that extra salt that you've dissolved will stay dissolved. If that's the case, that's called supersaturated. It's actually kind of cool because those solutions, they'll look like total liquid solutions, and then if you just tap them or add one more crystal of salt at room temperature or do something to disturb it, all of the extra salt will come crashing out of solution and make some pretty crystals. Anyway, so supersaturated solutions hold more than they should of the solute. They're unstable, okay, and they will precipitate out any excess solute with any disturbance. Precipitate means formation of an insoluble solid, okay, formation of an insoluble solid. That's what a precipitate is, just to remind you. Oh, this is just for pretty pictures, so you get a little break here. Sodium acetate is a very cool solution to make a supersaturated solution. And so what happened here is they added extra sodium acetate, let it cool down carefully without disturbing it, and then they probably stuck like this glass rod in and scratched the side of the container, and that causes all of these crystals to come out. It's very pretty. All right, so as I said a minute ago, solubility is the maximum amount of solute, okay? And one more vocabulary word. If two liquids are soluble in each other, like the alcohol that people drink, beer, wine, drinking alcohol. So alcohol and water are completely soluble in each other. We say they are miscible, okay? That's an important vocabulary word. So that only refers to two liquids when you say miscible, okay? If they are not soluble in each other, we say they're immiscible. So oil and water, again, two liquids. They're not soluble in each other, so we say they're immiscible. All right, what is solubility dependent on? I think it's intuitive that it's dependent on temperature, but it's also dependent on pressure. Primarily gas solubility is dependent on pressure. The units that you'll deal with, and I know there's actually one of the first labs you do has you convert solubility to these units, but this is just a real common kind of consumer unit that's used for solubility. Grams of solute dissolved in 100 grams of solvent. So it just happens to be, I don't know the history of that, but that happens to be a common unit. All right, so because the solubility of most solids increases as the temperature increases, we have something called solubility curves. They're pretty easy to interpret. You just have to be familiar with them, so I'm going to show you in a minute. There'll be a bunch of lines, and any place on the line represents the saturation point. Any area below the line refers to unsaturated situation. And if you happen to have a point above the saturation line, that would be supersaturated. So let's look at some solubility. Okay, so as we said, in general, this is solubility on the y-axis, okay, in those funky units, versus temperature. Okay, so in general, solubility goes up with temperature. Okay, these are upward sloping curves. Okay. The exception would be gases. And again, I think that's kind of intuitive. If you open a container of Coke, you know there's dissolved CO2 in it, and if you were to put that container of Coke on a hot plate, what would happen? You'd be bubbling out that CO2. So the solubility of gases goes down or decreases with increasing temperature. No surprise there. But almost every other material solubility increases with temperature. Let me go through one of these just to kind of make sure you can understand this. Let's say that I asked you what the solubility of sodium nitrate is at 50 degrees. What is the solubility of sodium nitrate at 50 degrees Celsius? How would you determine that? Well, you look for 50 you look for 50 degrees and you go up, find sodium nitrate. Here's sodium nitrate. It's red or orange, I guess. Anyway, so go up the 50 degree till you get to 50 degrees on sodium nitrate. And what is that solubility? It is, I would estimate about 112 grams of sodium nitrate can dissolve in 100 grams of water. Okay? And another question I might ask would be, could I dissolve 150 grams of potassium iodide in water at 0 degrees? Can I dissolve 150 grams of potassium iodide in water at 0 degrees? Well, the first thing you want to do is find potassium iodide. And we're talking about 0 degrees, so find 0 degrees and see what is the solubility of potassium iodide at 0 degrees. It is about, looks about like 128 grams of potassium iodide will dissolve in 100 grams of water. And this person's asking me if they can dissolve 150 grams. No, the answer is no. You can only dissolve 128 grams. Okay, so I had forgotten I posted this large one. It makes everything easier to see. Look at sodium sulfate. It's kind of weird. Its solubility goes down with increasing temperature, but it's the only one. I don't really know why that is, but that's a curiosity. All right, so at saturation, there is an equilibrium between the dissolved form of a substance and the undissolved form of a substance. It is a dynamic equilibrium, which means you don't dissolve everything you can and then movement stops. What happens is undissolved particles continue to dissolve, and soluble particles continue to reform and make the undissolved. So there's a back and forth motion in any solution equilibrium. So a molecule 1 minute might be dissolved and the next minute might not be. Might switch places with another one and might not be. So that is a dynamic equilibrium. You haven't really been introduced to equilibrium. It's a very important concept in this entire class. And so just to introduce you to it, equilibrium of anything means that the rate of the forward process equals the rate of the reverse process. So in this case, it would mean the rate of dissolving would equal the rate of precipitation. Okay, that's what equilibrium means. The forward and backward rates are equal to each other. So here's a visual of equilibrium I just talked about if you're more of a visual learner like me. So it shows kind of on a molecular scale what goes on when you're dissolving something. In the beginning, when you first introduce something like sodium chloride salt to water, these little things are water molecules, H2O. Kind of get familiar with what they look like. To me, they look like a Mickey Mouse head with ears. The little ears are the hydrogen atoms, and the red sphere in the middle is oxygen. And this represents sodium chloride. Okay, and when you first introduce sodium chloride to water, it can only go in one direction. The sodium chloride's dissolving. please remember, if you didn't know already, make note of the fact that when you dissolve a salt in water, what happens is the salt separates into its cation and anion. And the cation and the anion becomes solvated or surrounded by water molecules. It's a stabilizing attractive force. So if you look at one of these molecular representations, so remember that the Mickey Mouse heads, are water molecules, and you see they are surrounding or solvating the ions. See the green ion in the middle, and over here the purple ion in the middle. These ions are being solvated and therefore dissolving in water. So when enough of the sodium chloride dissolves and gets solvated, some of it begins to recrystallize or precipitate back into the insoluble form. So you have a forward and a reverse process going. When the rate of the forward and reverse process equal each other, that's called equilibrium. And that is the saturation point. Equilibrium occurs at saturation. All right, I think these are probably terms you're already familiar with, but just to make sure, okay. So now we're going to go pretty much into heavy theory of solubility. I mentioned earlier that what determines whether or not something will dissolve in a solvent depends on the intermolecular forces. The intermolecular forces among the solute itself, among the solvent molecules themselves, and then between the solvent and solute. So all of these attractive forces have to balance in order for something to dissolve. You may be familiar with an expression that says like dissolves like. If not, you probably want to make note of it. That'll show up in your lab too. What that means is that polar solvents will tend to dissolve polar solutes, and nonpolar solvents will tend to dissolve nonpolar solutes. That's because, again, of intermolecular forces. So another way of stating like dissolves like is substances that have similar intermolecular forces have strong attractive interactions and tend to form a solution. So let's look, for example, between ammonia, which is NH3, and water. Both of these are polar molecules. They both can hydrogen bond. Okay, remember hydrogen bonding is fun. If you have a hydrogen atom directly attached to fluorine, oxygen, or nitrogen, you can hydrogen bond. And so ammonia and water have very similar intermolecular forces, and so you mix them together, they're very soluble in one another, and that's because the attraction between them is so strong. All right, so just a kind of a checkpoint to see if you're getting what I say. Let's think of trying to dissolve iodine, molecular iodine. Remember, it's diatomic, so it's I2, in water versus trying to dissolve it in hexane, which is basically 6 carbons with hydrogen molecules. I'm not going to fill them all in. Okay? And so to answer that question, you would have to ask yourself, what are the intermolecular forces present in hexane, water, and iodine? I'm hoping that you know that iodine is nonpolar, that it only has London dispersion forces. I hope you've heard me in class. If you haven't, you need to make note of it. It's very, very important that carbon-hydrogen bonds are nonpolar. So if you have a molecule that is only made up of carbon and hydrogen, it is a nonpolar molecule. Doesn't matter if it's symmetric or not. The bonds are nonpolar, means the molecule has to be nonpolar. Water, of course, is polar and can hydrogen bond. So which of these do you think iodine is more likely to dissolve in? Like dissolves like, so iodine will be more likely to dissolve in hexane. All right, let me think a minute about trying to dissolve methanol in either water or another hydrocarbon called octane. I'm hoping immediately you'll see methanol as a polar molecule. It also can hydrogen bond, so it's definitely going to dissolve more readily in water than in the nonpolar octane. All right. Okay, so this slide you have to listen kind of carefully too. It's not hard, but it's detailed. So in order for something to dissolve in something else, this is what, whoopsie daisy, this is what must be overcome. The existing solute-solute attractive forces must be overcome. So that means that if you're trying to dissolve sodium chloride in water, the attractive forces that two sodium chlorides have between one another must be overcome. Otherwise, they're not going to want to leave each other to go into water. You also must be able to overcome solvent-solvent attractive forces. So if you have water as your solvent, they're obviously strong. Water molecules are strongly attracted to one another through hydrogen bonding. But if you're going to introduce a solute like sodium chloride, you need to overcome these solvent attractive forces too. Both of these processes of breaking up the existing intermolecular forces are endothermic, requiring input of energy. So why would anything dissolve in anything else if all it required was input of energy? There is a return on the investment, okay? And that is if the new intermolecular attractions between the solute and the solvent are strong enough, then the dissolution process will be favorable. So here you start out with your solute, sodium chloride, whatever you want to imagine, that has its own intermolecular forces. It's surrounded by the solvent, which also has its own intermolecular forces. If the interactions between the solute and solvent are not strong enough, they'll just keep separated. Okay, that's what happens when you add oil to water. But if they find out they have strong intermolecular attractions between one another, solvation will start to occur and dissolution will happen. So it really depends on comparing intermolecular attractions between the solvent solute and what they were before dissolution. All right, so just another way to visualize it. So you start with a solvent. You have to input energy, which is mathematically a positive sign. You have to add energy to break up the intermolecular forces in the solvent and solute. You mix them together. They will dissolve if the attractions between them are very strong, stronger in fact than the individual attractions before mixing them. So if mixing them together is exothermic, that means if it gives off energy, if it's favorable energetically, then dissolution will occur. We refer to the value, the overall net enthalpy of solution, that means the net heat change when you try to dissolve a solute in a solvent. So that is called delta H, either enthalpy of solution, or some people call it heat of solution. It means the same thing. Obviously, if you dissolve something in something else and it heats up, that means that overall it was an exothermic process. There's several off the top of my head, but I know sodium hydroxide is a huge one. If you dissolve that in water, it can get so hot that you can't even hold the container in your hand. It's a very, very favorable process. So what that would mean is the delta H of solution for sodium hydroxide in water would have a negative sign. Negative means energetically favorable, exothermic. Okay? All right, so yeah. I'm being redundant here. Exothermic, you'll see a negative sign in front of the enthalpy of solution. If it's endothermic, if the net process requires input of heat, you'll see a positive sign in front of it. And actually, there are some that'll still dissolve, but the container gets cold. What that means is that they absorb enough heat, enough energy from the surroundings, which would be the container, the air, whatever, the solution itself, to actually dissolve, but then it would feel cold to you because dissolving process has actually sucked in energy. All right, so this is just kind of a summary slide, more kind of like mathematical equations representing what I said. So the terms involved in dissolving something would be the enthalpy of separating solute molecules from one another. That's always endothermic. It always requires input of energy. And the enthalpy of breaking up the intermolecular forces in the solvent is always endothermic. The formation of new attractions between solute and solvent particles, if they do exist, would be exothermic. Okay, if you're going from no attraction to some attraction, it's exothermic. Now, whether or not the whole dissolving process is exothermic or endothermic depends on adding all of these enthalpy processes together. Okay, and if all together they are exothermic, then it will definitely happen. It's energetically favorable. If you add them all together and they are endothermic, sometimes it happens if it's not too endothermic, the container will feel cold. Sometimes you actually have to add extra heat to get them to dissolve at all. So, but this is kind of the mathematical description of dissolution. I think this is rather a redundant slide, so I'm going to go ahead and skip over it. All right, so here is a pictorial of the mathematical equation I just described, where the net enthalpy of solution depends on the enthalpy of breaking up solute intermolecular forces added to the enthalpy of breaking up solvent intermolecular forces added to the enthalpy of solution of solute solvent attractive forces. Okay, and all of those give you delta H of solution. Now, enthalpy of solution values would be what you would see in reference books at a particular temperature. Take a look at the diagrams. Make sure that you can interpret them. Again, I guess I'm very visual. These make more sense to me. The picture on the left is showing an exothermic dissolution. What that means is the energy required to break up the solute and solvent intermolecular forces is less than the energy gained back by the intermolecular attractions between the solute and solvent. So you see here, you have a net energy gain. Energy is released. You have excess energy. So the heat of solution in this case would have a negative sign. Energy would be released. The picture on the right, the energy required to break up the existing intermolecular forces in the solute and solvent is quite large, and the energy return you get back by making new intermolecular attractions between the solute and solvent is small compared. So in this case, you require more input of energy than you get back, and that's an endothermic situation. So the delta H of solution in this case would have a positive sign, and it would be an endothermic process. Okay, I mentioned this a minute ago, but it's very important to understand, and you might even be asked to draw a pictorial similar to this. So on a molecular level, if you try to dissolve an ionic compound in water, what happens when an ionic compound dissolves in water is the first thing it does is separate into the individual ions. And that is so the individual ions can become solvated or surrounded by the solvent, in this case water molecules. Take a look now for the cation, sodium cation. See how the water molecules are oriented around the cation. They're oriented so the electronegative end of the water molecule, that is the oxygen, is more electronegative than the hydrogens, are oriented facing the cation, okay? So that's what's stabilizing. On the other hand, the chlorine, which has a negative charge, it's the anion, all of the water molecules are oriented so the less electronegative hydrogen atoms are facing or closest to the anion. Okay, so again, opposite charges attract. That's what this picture is trying to show. So the better water can solvate or stabilize individual anions and cations, the more soluble an ionic compound will be in water. This is just kind of a blow up of the picture. When water is the solvent doing the solvation, it's often called hydration, so I just want you to be familiar with that word. So hydration really is salvation by water. This reminds me of a story when I was teaching in high school, and I was talking about introducing the term salvation, and one of my students finally asked me, are you saying salvation? Like you get salvation from, like in religious terms? And so which just tickled my funny bone. So at the time I'm like, okay, salvation is when solute molecules get saved by solvent molecules. Anyway, all right, hydration. And that is the end of part 1. There are 2 more lectures with chapter 12. So this first lecture is really just some terminology and introductory concepts. Expect a few multiple choice questions on this on your test, as well as possibly a free response explanation of one of the concepts. That's it. Make sure that you take the quiz that goes with this in learning catalytics.